usual with the ICAR CCPO seminar series. And I'm Tom Allen. I am the host and moderator today from ODU Geography and ICAR. With us is Dr. Manoochehr. I had pleasure of meeting and working with him in the last 2 years since he has arrived at Virginia Tech, that other campus, about the same longitude or latitude, but just west of us. He is a associate professor, specialist in satellite geodesy, modeling, coastal deformation of all sorts, and water resources. And today he's going to talk about one of those specialties of relative sea level rise. He has PhD from Potsdam University in Germany, master's in geodesy from Tehran University, and a bachelor's in surveying engineering from Amir Kabir University of Tehran. He directs a lab, does a lot of satellite synthetic aperture radar applications at Tech, and is with the Virginia Tech Center for Coastal Studies, I believe it's called now. Thanks, Manu, and take it away.
Thank you, Tom, and everybody else for the introduction and also for the invite. It's a pleasure to be here, and I'm going to share some of our recent works with you to hear. Actually, I want to hear what's your opinions and thoughts, and hopefully at the end, we can forge some collaborations through this kind of interactions. So I start my talk with. I hope you can see my slides.
Yep.
Yeah, okay. So I start my slides, my presentation with this slide that shows a few different hazards and disasters in play that impact the globe and planet as a whole. So they have socioeconomic impacts and the changed environment. To monitor these changes at the global scale, day and night, independent from the weather and climate, remote sensing, it seemed to be an efficient and cost-effective tool. And among those, we put lots of emphasis on active imaging technique called radar that transmit microwave signal that hit the ground and bounces back to the satellite. By collecting that return signal, we can tell something about the water coverage, forests and biomass distribution around the planet, but also we can use that to investigate geohazards such as volcanic deformation, as you see here, at Camp Gray, and many other applications that it's well beyond this presentation to discuss. And we use those data that are available to us to do lots of different kind of research. And here I would talk a few of them in a little bit. The good thing about radar is that radar technology from space, or radar remote sensing from space, is that plenty of satellites have been collecting data since 1992. So the record goes back at least 3 decades. And most of this data are available, at least the archive one. And among this, on this chart, you see different satellites with different wavelengths. Let me see if I can switch to pointer. Yeah, better. So there are, as you see here, there are different satellites with different wavelengths, starting from X, which is the shortest band, to the L, which is the longest. And the horizontal axis is the time of the launch, and the bar here shows the longevity of each mission. So some of these satellites are no longer active, but their data set is available, and for most part is not actually investigated. And anybody can access this data and do lots of good research with them. Among these satellites, there is actually two satellites, Sentinel-1A and B, has revolutionized the way that radar remote sensing of the Earth's surface is done because of their open data policy, that every image that is taken by this satellite in a matter of hours is publicly available to anybody around the world. Whether you are sitting in the United States, Virginia, or you are sitting in Iran or North Korea, you can access those data sets and do research and cool things with that. And hopefully NISAR that is scheduled to be launched in 2023, which is a joint venture between NASA and India, will follow the same policy and provide us with the valuable data that can be used for investigating Earth's surface and atmosphere at the global scale, but at the same time, very high resolution. So together with those state-owned satellites, we have also private sectors that are stepping up and launching many small sats that provide us data almost every day, 1 image a day from anywhere on the planet. And that data sets also are available at a very low cost to public, and some of those archives are also free. So the point is that I want to make is that we have plenty of data. Really, the point is not availability of the data, but is how to efficiently explore that data to answer big questions that are impacting us. So a little bit going back in time, about 28 years. So the SAR interferometry, the way we know it, started by this paper that made it to the cover of the Nature magazine. So it's a deformation associated with the Landers earthquake that was monitored or measured by using radar images acquired by the ERS-1 satellite launched by European Space Agency in 1992. So in the next few slides, I would explain in brief through the cartoons how SAR interferometry works for some that may not be familiar with the technology. So consider this Hawaii Island, including 2 active volcanoes, Mauna and Kilauea, is going to be a subject of the monitoring using radar. So satellite flies over the region, transmit the radar signal and collect the backscatter and generate the first image, then goes away and comes back days later, weeks, days, months later. And at the position that is close to the first one, but not identical often, transmit the same radar signal and illuminate the same area. So we are left with these 2 images, so image 1 and image 2. To create an interferogram, we multiply the first image with the complex conjugate of the second one. And in this way, we create 1 interferogram. And this interferogram contains information related to the change in the surface elevation, as well as the atmospheric turbulences and artifacts, and elevation and the topography of the ground. And that's because of the radar geometry. So satellites sees the same topography from 2 different perspectives, and that causes a sort of artifact that has to be removed. So to remove the effect of the digital elevation model and create a differential interferogram, we usually use available DEM, such as SRTM-DEM. We subtract this RTM-DEM from your interferogram, and then we create a differential interferogram. What you see here is mostly the formation of the ground. For example, here is due to volcanic activity at Mauna Loa and Kilauea. And I would like to bring to your attention, this is radar coordinate, is not in geographic coordinate. That's why the volcano is to the other side. The Kilauea is to the other side. But also we see some signals, some phase changes specifically here that cannot be associated to any surface deformation. Those are likely to be due to the atmospheric delay, which is caused by the difference in atmospheric properties, pressure, temperature, and humidity between 2 acquisitions that has to be removed. The other point that I want to emphasize is that InSAR measurements are not vertical or horizontal, they are in line of sight. So 3D displacement of the ground is projected on the line of sight. And what we measure is a movement toward the satellite or away from the satellite. This is also important when you come to the interpreting that data set. So the next big thing was the permanent scatter, or in general, multi-temporal InSAR. So satellites fly over the same area and collect many, many images, tens, hundreds, sometimes images. Combining those many images over the same area provide us with the redundant observation time and space that allows reducing environmental artifacts. And as a result, we can create the deformation maps that are much more precise than individual interferogram. So this is the first time, the first demonstration of that advancement was done in 2001. Since then, there has been plenty of new methods and techniques introduced through different literature. One of those is the method that we developed in our lab. We call it WAB InSAR, and it's a algorithm that I explained here, relies on a wavelet multi-resolution analysis. In simplistic or schematic view, we have a stack of the SAR images, we send it through this wavelet domain, and we decompose into its building blocks based on their frequency properties. And then we apply some statistical analysis, statistical test to identify different components such as orbital error, atmospheric delay, phase noise, and so on. And after identifying those artifacts, we toss them, we throw them out, and then we apply an inverse wavelet transform and create a deformation map that is precise, accurate, and it's therefore not affected too much with the atmospheric, the environmental artifact. And detail of it is discussed in these papers, and I would be happy to answer any question if you would be interested more. So some application would be the relative sea level rise. It's a topic that I would like to focus on. Everybody knows, I believe, on this call that sea level is rising due to a number of reasons: density change, winds, discharge of the terrestrial water, ice melting. But also, I would like to emphasize that land also is subsiding. So, and there is a parameter called relative sea level rise, which is the difference between the surface of the ocean or water surface and the height of the land. And that's a parameter that is of practical use for hazard analysis. And those who live near the coast often are concerned with this parameter rather than sea level rise alone. In this slide, I want to highlight why the land subsidence is important. So there is a study suggests that the frequency of flooding around the United States will be doubled if the sea level rise locally 10 to 20 centimeters. So the yellow line shows the rate of sea level rise at the Galveston, Texas tide gauge. So we see that that limit of 20 centimeters will be reached about 2040 if there would not be any subsidence happening. But we know that the tide gauge is affected by about 3.2 millimeters of the land subsidence. So adding that land subsidence, that threshold of 20 centimeters, 200 millimeters is reached in 2025. So it means we have 15 years less to prepare for that intensified flooding hazard. So this just simple example, I think, will highlight the importance of land subsidence. And if you look at the recent projections published in IPCC, within the next 40 years, even if you look at the worst scenario, SSP 5, equivalent to RCP 8.5, within the next 40 years, actually, the rate of sea level rise is not as much. And in many places, land subsidence is the dominant factor driving the relative sea level rise. And those factors or those forcing elements that causes the accelerated sea level rise would kick in after 2050 and 55 and 60. So again, I want to emphasize land subsidence is a key factor that has to be accounted for evaluating the flooding hazard in coastal areas. So what drives the coastal land subsidence? So in general, land subsidence. This is a cross-section through United States from the West Coast, Cascadia, all the way to the East Coast, basically where you guys are. Different factors affect different parts, and in some area we have superimposition of multiple factors. So starting from the west to the east, the faulting or tectonic process is the main driver in Cascadia and west coast of United States, driving the land elevation change. During the interseismic period, due to the compression or squeezing the overriding plates, it thickens and uplift happens. But during that earthquake, most of that uplift is released in the form of horizontal movement and some land subsidence. So we would expect to see a massive land subsidence during next earthquake at Cascadia, which has to be accounted for when we develop flood resiliency plans for that region. So the other process is the compaction of the aquifers that due to the pumping of the fluids, whether it's water or hydrocarbon. This process is very localized compared to the previous one, but it can be very fast in time and space and and causes significant land subsidence. The other process that is in general very slow and impact large areas is the GIA effect. And where the mass is lost, we have uplift of up to 1 centimeter per year. And in the perimeter of that mass giant glacier, we have a gradual uplift of 1 to 2 millimeters per year. And the last process is the compaction of the sediment. So the sediment, when they are deposited under their own weights, they begin to compact. And this compaction can be also non-linear in time and space, depending on geology and the rate of the compaction and sedimentation and so on, and type of the material. So putting everything in perspective of sea level rise, here this graph shows the different factors and drivers of the land subsidence, their rate, and also their time scale that they impact relative sea level rise, and compare them with the rate of the sea level rise and its projection that is shown here. Anything that is to the right, including sediment compaction and fluid extraction, has a rate that is faster than rate of sea level rise in most places, and it impacts the coastal at a short time scale as well. While anything is to the right, to the left, sorry, and up, are those processes that are not as important as sea level rise within 21st century. That would include, for example, sediment loading and GIA effect. So we have some challenges. We would like to have observations that are extensive, especially, but also high resolution to be able to use them for management relevant planning. And this, and also observation should be related to the global reference frame to be able to compare it with observation of the sea level rise that are often coming from or presented in a reference frame. So these challenges present us with the opportunity, and that opportunity is to combine or to collaborate to forge collaboration between two communities, which one is the SAR interferometry and the other one is the GNSS community. GNSS measurements provide us with 3D vectors that is stable in time and also refers to a reference frame, while InSAR observations are extensive in space, but they are inherently local measurements. And as a result of this combination, we might be able to address those challenges, as I will show you in a few examples. So take-home lessons so far. So land subsidence exacerbate the hazard and risk associated with sea level rise. Several natural and anthropogenic factors drive land subsidence, including tectonic aquifer, reservoir sediment compaction, GIA and SIA, sediment isostatic adjustment. And InSAR enables measuring the contemporary rate of subsidence at management relevant resolution. So when we want to talk about the future and future hazards, we have projection of the sea level rise. But the point is that we would like to have also, we need projection of the land elevation as well. And these projections in principle or in theory can be obtained by using models that are calibrated using present day observation of the vertical land motion. And then you project it forward and you get the estimate of the vertical land motion in future. But in practice, this task is challenging because most of the forcing factors that drive vertical land motion, such as groundwater and hydrocarbon extraction, are non-linear and depend on the economy and also population distribution and climate factors. So this has remained challenging. I would like to show you in the next few slides some of those challenges that are investigated in different cases. So here is an example of the GPS station at the Cascadia that is uplifting at the moment at the rate of about 2 millimeters per year. So, and that site has been affected by a co-seismic major subduction events about 200 years ago. And this graph shows the simulation of what would happen if the earthquake would strike 200 years later in 1950. So all the uplift that is accumulated over the past 200 years would be reversed in terms of and will be turned into about half a meter of subsidence, which will be followed by a slow post-seismic relaxation and after sleep that eventually reaches the same level. So the challenge with this, identifying this step here is that to know when that happened, we have to predict earthquake. And science of earthquake prediction still is far from this stage. So it remains very challenging to know when and how vertical land motion due to tectonic processes evolve. This is an example from Taiwan that there is aquifer and there is very good data sets to quantify dynamics of that aquifer using a pure mechanical model. So authors chose 5 years of data and created a model. And within that 5 years, we have normal precipitation and try to predict how the vertical land motion looks like in the last year when we had low precipitation. We see that even for this fairly simple case, the model failed to predict correctly the deformation or land subsidence in the 5th year. And that because of the non-stationarity of the processes that drive the compaction of the sediment, compaction of the aquifer, sorry. The less challenging task probably is predicting the GIA effect. This is an example map of the GIA model, shows subsidence that impact most of the Canada and higher latitudes, and the rest of the, uplift that impact Canada and higher latitude, and subsidence that impact most of the east coast of the United States. And if you go away from the zone that ice mass is lost now, like Greenland or the Alaska, in most places, the rate of the vertical land motion due to GIS seem to be steady in the 21st century. So therefore, this is not a challenging task. The medium challenging task is the predicting the compaction of vertical land motion due to compaction of the sediment. This is a model, it's a mechanical model, relate the thickness of the sediment to the age of the sediment and the rate, which is the color code for each pixel. So you see that the younger sediment, thicker sediments have faster rate of compaction than older and thinner sediments. So this shows that compaction of the sediments can be especially variable and the rate might be heterogeneous, but in general, for the time scale, it can be considered steady. So take-home lessons for this section. Future work is needed to develop multi-objective land subsidence forecast models that integrate the underlying physical processes with socioeconomic and climate forcing and are calibrated using contemporary observation. This is really to match the projections of the sea level rise that are very well established and widely used for the hazard modeling. A few examples of the combination of the InSAR and GPS or GNSS measurement to measure the coastal vertical land motion. Here's an example from the coast of California, about 1,300 kilometer long coast. Here you see that each of these rectangles is a frame or footprint of a frame of a SAR satellite. We use Sentinel and ALOS data, and each triangle is the GNSS station, and the red lines are the active faults in the region. So here I show you just the final result, which is a combination of all that data set I showed in the previous slide. So the blue means subsidence and the red is uplift. In this case, is no longer in line of sight. It's projected in a vertical direction. So in the Southern California, in general, we have subsidence, and also in Central Park, we have another zone of subsidence at the rate of up to 5 millimeter per year. In the Northern California, we have uplift, which is mostly due to the uplift at the Cascadia subduction zone. And here in between, we have another zone of uplift, which is likely to be due to faulting processes. There are a few zones of uplift here localized, as you see here. This is Santa Ana, Santa Clara, and also Livermore aquifers that are recharging following a drought season due to water management efforts, and also actively injecting fluid in the ground, treating water and injecting it back in the ground. So as a comparison, as a validation test here, we compare InSAR measurements with values of the GNSS station. Each dot is two value. The field value is the GNSS rate, and the rim is the VLM velocity. So the area that you don't see the difference between the two color means InSAR and GNSS match very well. And some area, for example, here, if I point out, you see quite a bit of difference between the two. And that means InSAR and GNSS don't measure the same value. And that's mostly because GNSS and InSAR don't cover the same observation period. For the stations that cover the same period as that of InSAR, we found a standard deviation of the difference, which is less than 1 millimeter per year. Using that data, we estimated also exposure to land subsidence for the California. And we see some counties, what you see here is the communities, some communities are more affected with the land subsidence than others. And mostly those highly exposed to land subsidence, including San Francisco Bay Area, LA, and San Diego. We estimated several million people were affected or exposed to land subsidence of faster than 1 millimeter per year during this observation period along the coast of California. Here are some more take-home lessons. Combination of the multi-track InSAR and GNSS data enables measurement of VLM at thousands of kilometer extent and 50-meter resolution and millimeter accuracy. We created the first map of the vertical land motion along the coast of California in global reference frame with respect to the IGS. And at the management relevant resolution, we estimated about 4.3 to 8.7 million people are exposed to land subsidence in the region. And the last one that I want to draw your attention is that SAR data with global coverage are publicly available. And it is technologically feasible to compute worldwide map of vertical land motion at management relevant resolution. Just we need a will and from private and public sectors investment to make this happen. And I think this is something we should push for it. And we are in the community, we are insisting that this has to be done. And I'm hoping that sooner or later this will happen. Some more applications. So now I'm zooming into the San Francisco Bay Area. That's where we have the subsidence. At the moment, I'm just showing you subsidence, and I left out any zone that is not subsiding. So fast subsidence, zone of fast subsidence subsidence are San Francisco International Airport, Foster City. This is where Facebook headquarters is located. I'm not really worrying about that if it gets flooded, and a few other places that you see here. And also we have the projections of the sea level rise. These are the results published in 2017. At the time, they used still RCPs. Combination of this and projection of the vertical land motion or subsidence allows us to estimate flooding hazard for the region. For that, we need to know how land subsidence evolved through 21st century in the Bay Area. For that, we created a mechanical model that relates the compaction of the sediments, as you see the color, to the age of the sediment, horizontal axis, and thickness of them. We found that for most places, we can assume the rate of subsidence is linear in time. And if you make that assumption, the error that we cause is going to be 5 to 14%, which is negligible compared to other range of errors. So therefore, we linearly extrapolated the subsidence through 21st century. So we tested many different scenarios. Here, I just show you the result for one scenario, RCP 8.5. Under this scenario, we estimated the sea level rise would cause area of 168 square kilometer to be flooded. And if we add local land subsidence to that, the area of the flooding would increase to 218 square kilometer. So what you see here also in this figure is that area that's going to be flooded only due to the sea level rise, and those that's going to be flooded due to sea level rise and local land subsidence. So the yellow is only sea level rise, and the reds are area that's going to be flooded due to sea level rise and land subsidence as well. Next case study is Houston, Texas. We performed the same analysis in Houston, Texas. We used a high-resolution digital elevation model from LiDAR and builds of satellite data from Sentinel and ALOS, and we created a map of the vertical land motion, as you see here. So most of the area is affected by subsidence of up to 5 millimeter per year, but in most places 2 to 3 millimeter. So combination of the vertical land motion rates and high-resolution digital elevation model from LiDAR and projection of the sea level rise, and here we added a storm surge projection for the analysis. We create a different scenario of the flooding through 21st century. Here, I'll show you one example by 2100, assuming that sea level rise magically stops. And what you see here is the area of the subsidence due only to the compaction of the land subsidence, which is mostly due to compaction of the sediment aquifers. We estimated about 76 square kilometers going to be flooded due to only land subsidence. And the other end member scenario is that we have meters of sea level rise under the RCP 815, and we have 8 meters of the storm surge, which is comparable to that of Harvey. Hurricane hit the region in 2017, as well as the land subsidence on top of that. The total area of the inundation increases to 1,156 square kilometers. And we tested, of course, wide range of scenarios, and we have created a table for that, but I don't present that here, but I encourage you, if you would be interested, you can find the detail in this study. So take-home lessons. Even without any future global sea level rise, flooding hazard may increase due to continued land subsidence. This is very important, that land subsidence alone would exacerbate the flooding hazard. In San Francisco Bay Area, an area of 125 square kilometer to 429 square kilometer will be subject to inundation and flooding by 2100 under different scenarios of the land subsidence and sea level rise. In Houston, the area would be 1,186 to 1,157 square kilometers under different sea level rise, land subsidence, storm surge scenarios. In the next few minutes, I just walk you through a few ongoing projects that we are doing now. So one of the projects is monitoring major airports. So we are contracted to monitor about 20 major airports at the high resolution. For the, this year is infrastructure year. So airports are major, very important infrastructures that their stability and also possible land subsidence has major impact on the quality of the service that they offer, and it's directly translated into significant loss if, for example, flights are delayed or canceled. So to the left, you see San Francisco International Airport, rate of the subsidence between 2017 and 2021. Some area, for example, here is subsiding at a rate of almost 1 centimeter per year, which is mostly due to the landfill compaction. To the right is the Reagan National Airport, and we see that subsidence happen in different parts of the airport, specifically here in the south. I think it's a parking lot and part of the runway, but also here is a sea wall or flood walls that are subsiding at the rate of up to 5 millimeters per year. And you see here is a time series of the subsidence at this southern part here that has a very typical pattern of exponential decay associated with compaction of the sediments, very well known in the literature. So the other ongoing project, which is a sizable project in collaboration with USGS the title is Future Coastal Hazard in Southwest, a Coastal Change Hazard Template for the National Expansion. So in this project, we are using the best available science together with many different physics-based model of the sea level rise, storm surge, and land subsidence to evaluate future flooding hazards in the southeast and in general east coast of United States. And that's going to be a template that we're going to later expand into entire country once the models are tested and results are evaluated. So this is a work that is done by my graduate student, Leonard. So we just finished processing all the data along the east coast of United States. I think you guys are somewhere around here in Chesapeake Bay area, I believe. And we combined all the GPS data with data measurement from Sentinel and ALOS. And we created a map of the vertical land motion as you see it here. The precision of this map or accuracy in comparison with the independent data, GPS data, is about a millimeter per year, which is remarkable precision. In some areas you see here, Chesapeake Bay are subsiding at a rate of up to 5 millimeter per year. In some area here in the, I believe it's Savannah, somewhere around here, and that's also subsided at a fast rate. And later we are studying the causes and drivers of this land subsidence and associating that with different type of land use, land cover, and socioeconomic factors. So then another ongoing project is really to creating SSP-based projection of coastal land subsidence. So the really objective is to create a projection of the coastal vertical land motion within a baseline world. And those baseline worlds are defined by the shared socioeconomic pathways introduced in recent IPCC reports. And the goal is to have projections that are comparable to projection of the sea level rise to be used for different kind of hazard evaluation. So for that, we are now working with computer scientists to develop machine learning frameworks. One example is here that uses the multi-headed conditional variational autoencoder. The input to that would be projections of the land cover, land use, population, land temperature, precipitation, and geology of the region, as well as the present day measurement of the vertical land motion. And the goal is to project this observation of the land subsidence through 21st century at the scale that is relevant for planning, so 10 years, 20 years, 50 years, and possibly 100 years. And we are using different machine learning, other machine learning tools like UNet and so on. So I just put one example of the flowchart. We are hoping to have this results ready within a year as well. So here I would like to close my presentation. Thank you for your attention, and I would like to have answer any question you may have.
Thanks, Manoochehr. Lower your volume because of the applause. Now, it's a virtual conference, so this is a good opportunity. I haven't seen any questions on the chat, but if anybody would like to drop one in or let us know, you can unmute and we'll try to let you get a few in there. I certainly have plenty. Maybe I'll do the icebreaker question. I guess it's kind of actually the last slide was new to me, and you showed the kind of potentially machine learning algorithm to detect or explain some fine scale patterns of subsidence. And when I think about Norfolk, a lot of us around here think about issues. There's one clap. Issues of land use, history. Before the call, we talked about the historic dredge and fill operations. Do you think that the system, either the next generation satellites, or do we need more in situ sensors and GNSS could be able to be done, support land use planning at kind of a fine city scale to factor in subsidence specifically?
Right. The tools that we are developing is really capable of doing that kind of work. So basically, if the new data is available, so at high resolution or new type of data is available, we can integrate that into this autoencoder framework to update the projections. So it's an active learning system. So actively learn with the new data. So, and more data, the better it is. So there's no question about that. So at the moment, for example, for projections, we are using the models that are produced under the different SSP scenarios. So for land cover, land use, there are a few projections, and we have no idea how good they are. They're just models that's published within the last 2 years. And if we can revise that and update those models using new, for example, in situ measurements or new satellite data, the projection should improve over the time, definitely.
Mm-hmm. Yeah, I'm thinking about the, we have the outliers of like, we have a massive dredge spoil island called Craney Island. It would certainly stand out like a sore thumb. Brett Bezanga has done some research here, as I'm sure you're aware, but also just the major massive infrastructure of, the airport, the 6 marine terminals, the ups and downs of the coal mountains that are being dropped out here, the 2 coal terminals. This is a great test bed area for this. So if others on the line are interested in this, follow up with either me or put you in touch with Manu on that kind of specific research. How about any other questions?
Yeah, Tom, this is John. Quick question. Hi,
Yep.
Manu. Thank you. Thank you for your presentation.
Hi, John.
Hey, I'm curious about the projection into the future. Is that maybe this is a geological question, but it would seem that most of the water use, water extraction, compaction, and all of that should be relatively simple to just extrapolate into the future. So I'm wondering what's different that requires you on kind of an annual or decadal basis to keep changing things to do new subsidence? Why is it so hard? Sorry.
Right. Specifically, I would like to emphasize that the water use is extremely nonlinear in time.
Sure. Okay.
So that's the biggest challenge, and also the development of the structures. Like when you, for example, build a dam, you change the supply of the sediments to the nearby basin coast, and that would change the rate of the subsidence. And we don't know. So we have a component of the socioeconomic and population, and then we have a component of technology. Because when you build a dam, usually the purpose is irrigating farms and creating electricity, right? And that is really driven by the change in the socioeconomic factors and also migration of the population. So that's an extremely complex process to include into any process-based model. So that's why, for years we tried process-based model. We have some, limited success in an area that population is fairly steady, and the economy does not change rapidly. People don't switch from agriculture to, for example, manufacturing, etc. But in area like Norfolk, the region that are very active, and over this time scale of 10 to 20 years, people change the way they live. And that seemed to be very challenging to extrapolate into future.
Right. Thank you. I have one other question, if I may, which is probably an equally stupid question, but you're looking at radar reflectivity and with very small vertical changes. And so does the radar reflectivity change based on soil drying or vegetation changes? I'm sure it changes due to building and tearing down. So I'm just wondering, how stable is the radar reflectivity that you're using to get the interferometry?
Yeah, that's a great question. So radar signal is very much affected by properties of the surface. Whether it's the vegetation or change in soil moisture, or changing the roughness of the surface and so on. So what we do is we define a statistical test that allows for a certain tolerance. So for example, if the pixel is bare land and then there is a very mild or minor amount of grassland on top of that, and then again, a slight snow, we keep those kind of pixel. But if the land changes, so for example, there is no building and suddenly a building is created or built there, those pixels we toss. That's why our map is not continuous. So we have gaps, but our algorithm is robust enough to identify good pixels that have very decent distribution. So on average, we can identify a pixel every 70 meters, 73 meters to be exact.
Okay. Yeah, no, that's very encouraging. So it means that we can keep doing this for some time into the future and depend on the results, which I knew was the right answer, but I wasn't sure quite how that worked out. So thank you very much.
Thank you for the question.
Hey, Manu, I have a couple of questions.
Hi, Brad.
Great talk. Thanks. That was awesome. Yeah, building on John's first question a little bit, I had the same question, and that was what you're doing sounds really interesting and innovative. I'm wondering if within the the SSPs, how you can vary them in order to get some kind of uncertainty or some kind of bound on your future projections. And
yeah,
are they huge?
Right. If you look at, probably still you can see my slide, which is shared. So
Yeah.
we have a very significant, specifically use this autoencoder structure that has, the projection in the latent space, which governed by the multivariate normal distribution. So through sampling that distribution, we are able to estimate uncertainty or basically distribution of the unknowns, which is our projection. And as you expect, as it go forward to the future, the uncertainty increases and increases. And the uncertainty we get from this is wider, or uncertainty range is wider than the one that comes out of the sea level rise projections. So because we include more factors in it and we have more uncertain parameters than what is considered in sea level rise projections, it doesn't mean that their estimation is less uncertain. It's just the way they do that. So we, at the moment, this is really a new work. It's just we are beginning it, and I'm not aware of any similar work that has been done. And we need really more people to think about this problem and give us inputs to turn this into something that is comparable in terms of maturity with that we have in the sea level rise part of it, or ocean side, or let's say.
Yeah, no, that's really interesting. And then just a simpler question. When you showed the California map with the GPS stations and the agreement, did you use any of those stations in referencing to the vertical, or were you able to just?
What we do is we split the data set into a Thai data set and the Czech data set. The Czech data sets are not used in any analysis, including the one that, for example, you see here. This GPS station, the circles are GPS stations which are not used in any ways in analysis, and just we use them for validation of the result.
Yeah,
and that's what I reported. That 1 millimeter per year standard deviation of difference is for the data set that are not used in the analysis.
Right. Cool. Thanks.
I put a link to the paper, Miller and Shirzaei, in the chat box for those that AGU paper. So folks might want to check that out. I'm very interested in that very bright dot around Savannah and what that means in terms of a socioeconomic pathway. So I'm going to read that myself. I'm suspicious of the port, but there's also the Barrier Islands and dredging and some other things going on around there that might be a good comparison to here. Does anyone else have a question? Burning? We still have a couple minutes.
Yeah, Tom, can you hear me?
Yeah, Jim, go ahead.
Yeah, we're kind of in an interesting area with subsidence because we've got the two big plants, the paper mills that are really sucking water out of the aquifer like crazy. And now we've got the Hampton Roads Sanitation District is going to put water back. So it really makes for an interesting picture as far as trying to predict local effects. And I was just wondering, I didn't quite get what's the resolution of the method from the satellite data? Is it?
So pixel size, to be exact, for Sentinel, pixel size is 3.5 meter by 12.5 meter.
Oh, okay. Yeah.
So, but usually we average them, or we call it multi-looking, to increase the signal to noise ratio. So for the airport example that I showed you, the pixel size are 15 by 15 meters. So that's seem to be the best resolution you can get.
It's pretty good. And the other thing is on Craney Island, that north levee of Craney Island has been sinking for years. They keep adding to it. And the thing is probably 150 feet high, but most of it's underground.
Okay.
Who knows where it's going?
Which island is it? I mean, I don't know. I probably cannot point to the map, but
It's the Corps of Engineers disposal area. It's that big rectangular area that you see just north of Portsmouth.
okay,
Out in the Hampton Roads.
right.
Yeah,
And,
it's the corner where the James River meets the Elizabeth River. So
Okay.
if that helps you at all.
Yes. No, I can tell. Interesting. Okay.
Yeah, just to follow up on Jim's comment, though, is that it was actually designed by the Corps of Engineers to compact. So it's doing exactly what the engineers designed it to do. So no one should be surprised about that.
yeah, they've actually put in a lot of technology in there to try to accelerate the compaction with subsurface drains and wicking and all sorts of stuff. I mean, it's kind of amazing. But
They want the sediment. They want the sediment to go away. So it's sort of a sediment trash can for them. So it's doing what it's supposed to do.
Okay. Thanks, Tom.
Yeah, there's some notions that the port might develop it. But and another certainly a bypass anyway for some of the trucks on Hampton Boulevard. The
That would be
Pinner's
nice.
Connector and other things.
Yeah.
That's getting maybe out into the distant future.
Well, the political atmosphere there is a real tough one. Just sort of make that general statement. They've run across that before.
Anybody
Great.
else? No, I don't want to call anybody out, so I think we'll leave it at that. And then a couple closing comments. We have a CCPO ICAR seminar again next Monday. So that's on Southern Ocean biogeochemistry. Sean Henley from University of Edinburgh. And then 2 weeks from today, Dr. Scott Curtis from the Citadel, close friend of mine from my ECU pirate days. He's going to talk about comparative coastal water hazards. So you'll see a little more of this, and be interesting to get his reflections from Charleston, South Carolina in particular, as he heads the Charleston Climate Center. And I think we have one more right before the holiday, Thanksgiving, if I recall. So you get your money's worth here in the CCPO ICAR seminar. Thanks again, Manu. Learned a lot, and it's a lot of research frontiers. I'll catch up with you here shortly, but everybody, thanks for coming.
Yeah.
Thanks,
Thank you
Manu.
very much.
Thank you, Manu.
Appreciate that. It was great
Enjoy.
seeing you. Yeah.
Yeah, thank you.
Thanks.
Thank you very much.